Now I need to explain this question. Why these two functions form a basis of the solution space. Yeah. Because they have the same denominator, right? Yeah. So same denominator. Yeah. Yeah. And when we consider if they are a basis or not, we look at the linear independence, right? Yeah. So linear independence. When we do that, we can use a simplified version. We do not include the denominator. Yeah. So we only need to consider if cosine of x and sine of x together form a basis or not, if they are linearly independent. Yeah. So here I copy the definition of linearly independence, the definition. Yeah. Assume y1 function and a y2 function are linearly independent. Then there do not exist k1 and k2 such that k1 y1 plus k2 y2 equals 0 for all x on certain interval I. Yeah. So here, yeah, I realize these k1 and k2 cannot, there is a condition, cannot be both 0. Because if you make A1 and A2 both 0, obviously it is 0 on any interval I. Yeah. That's not allowed. Yeah. So here we need to, so K1 and K2 cannot be both 0. Okay? At least one of the two numbers is non-zero. Yeah? Under that condition, then you can say this. Okay? Yeah? All right. So, yeah. With this, because this condition is important. Yeah. Yeah. Here, we want to prove this form of basis. We use the contrapositive method. Okay? Contrapositive method. Yeah. So here, I prove it by the contrapositive method. All right. Yeah. Let's assume. Because our goal, so linearly independent, right? Linear. So here, we want to assume they are linearly dependent. How about that? Then we want to get a contradiction. Or different. You're not linearly different. So, yeah. So here we assume. Yeah. So here, assume there. Yeah. Because here they do not exist, right? So assume there exists K1 and K2 such that K1 Y1, yeah, so here K1 Y1, let's just use cosine of x plus K2 sine of x equals 0 on certain interval I. Okay? All right? Yeah. Then we want to get a contradiction. Yeah. Then we want to, so the contradiction actually, K1, K2 must be both 0. Okay? That's our contradiction. Yeah? Yeah. If we have this condition, then we will show K1, K2 must be both 0 there. It's not allowed, right? Yeah, it's not allowed. So then our assumption is not true. So that means that does not exist such K1, K2. Okay? All right? Yeah. Yeah. So we have this equality, right? Yeah. Because on all x on the interval I, it's true. Then let's take a derivative of this equality. It's also true, right? Another equality. So we take the derivative, we get another equality. So let's look, what's the derivative? Cosine derivative negative K1 sine of x plus K2 cosine of x equals 0. Okay? Yeah? See? Yeah. All right. Now, what do we get? Yeah. Is it possible? Yeah, so here, we have a linear system, right? Yeah. K1 cosine of x plus K2 sine of x equals 0. K2 cosine of x minus K1 sine of x equals 0, right? Yeah. All right. Yeah. We want to see what can we get. Okay. All right. From the first equation, K1 cosine of x equals negative K2 sine of x, right? Yeah. Let's look at what is tangent x. Tangent of x equals sine of x over cosine of x equals, here, negative K1 over K2, right? Yeah. From second equation, we have K2 cosine x equals K1 sine of x. Yeah. What is the tangent x from second one? Second one, tangent x sine x over cosine x equals K2 over K1, right? Yeah. So tangent x here, tangent x, they should be the same, right? Yeah. So these two ratios should be the same. Yeah. So let's put together. Negative K1 over K2 equals K2, positive K2 over K1. Okay? All right. Then let's do this multiplication. So we get negative K1 square equals positive K2 square. Yeah. Then K1 square plus K2 square equals 0, right? Yeah, K1 square plus K2 equals 0. Then K1, K2, because K1, K2 must be real numbers, right? Real numbers. Yeah. And sum of two squares of real numbers equals 0. Then they must be both 0. Yeah. K1, K2. So K1, K2, both 0. Then we get a contradiction. Yeah. Okay? So So have to both 0, then, yeah, assume, yeah, so here, yeah, let's do this. Assume there exists K1, K1, T2, not both 0, okay? Yeah, yeah, because they're not allowed. Not both 0, okay? Then, so the contradiction is here, okay? Yeah. Yeah. Because we get contradiction. In our assumption, we do not allow both 0. Yeah. Actually, yeah, to be more rigorous, we want to assume, yeah, both non-zero here. Make it stronger. Both non-zero. Yeah, because if one is 0, one term is gone, the remaining equals 0, but the cosine is not 0, right? Yeah. Only for small number, some scattered x values 0, but all the remaining values are non-zero. So then, if one is 0, one of the k is 0, the other is also 0. So here we assume both non-zero, right? Then here we got a both must be 0, so contradiction, okay? So contradiction. Then by this contrapositive method, our assumption is incorrect. Assumption incorrect, then the origin, this statement is correct. Right? Linearly independent. Linearly independent. Yeah. So we prove it. Okay? Here, we use this way, we prove it.